Welcome to an exploration of supercooled liquids, where water defies our expectations and remains liquid well below freezing. Imagine a bottle of water at -5 degrees Celsius that remains perfectly liquid, defying the intuition that water freezes at 0 degrees. This phenomenon is called supercooling. Let's start by understanding what supercooling actually means. Supercooling occurs when a liquid remains in the liquid state below its normal freezing point without solidifying. This only happens when the liquid is extremely pure and completely undisturbed, with no vibrations or impurities. Here's a thermometer showing water at -3 degrees Celsius, well below freezing, yet the water molecules remain in liquid form, moving freely. Common examples include purified water in clean bottles, beer in sealed containers, and even pure fruit juices. Before we understand supercooling, let's review why water normally freezes at 0 degrees Celsius. The key is Gibbs free energy, which equals enthalpy change minus temperature times entropy change. At 0 degrees Celsius, the solid ice and liquid water phases have exactly equal free energy, creating equilibrium. This graph shows free energy versus temperature. The liquid line and solid line cross at 0 degrees, where both phases have equal energy and coexist. The free energy change for freezing equals 0 at 0 degrees Celsius, marking the equilibrium point. The secret to supercooling lies in understanding nucleation barriers. Here's a key question. If ice is thermodynamically favorable below 0 degrees, why doesn't supercooled water freeze instantly? The answer is that freezing requires forming a critical ice crystal nucleus, which has an energy barrier. The free energy of a nucleus equals -4/3 pi r cubed times the volume free energy change, plus 4 pi r squared times the surface tension. This shows the nucleation barrier. The free energy first increases as a tiny ice cluster forms, reaches a maximum at the critical radius, then decreases as the crystal grows. For small ice clusters, surface energy dominates and makes them unstable, so they tend to melt back into liquid. Only when a cluster reaches the critical size can it overcome the barrier and grow spontaneously into a full ice crystal. The critical radius equals 2 times surface tension divided by volume free energy change. Let's do a numerical calculation to understand how cold water can get before freezing. The volume-free energy change approximately equals the latent heat of fusion times the temperature difference divided by the melting temperature. For water, the latent heat of fusion equals 334 kilojoules per kilogram. Converting to volume units, this equals 3.34 times 10 to the 8 joules per cubic meter. At -5 degrees Celsius, the temperature difference from freezing is 5 Kelvin. So the volume-free energy change equals 3.34 times 10 to the 8 times 5 divided by 273, which gives approximately 6.1 times 10 to the 6 joules per cubic meter. The surface tension between ice and water is approximately 0.033 joules per square meter. Therefore, the critical radius equals 2 times 0.033 divided by 6.1 times 10 to the 6, which gives approximately 1.1 times 10 to the -8 meters, or 11 nanometers. This tiny critical nucleus is only 11 nanometers across, containing roughly 40,000 water molecules arranged in ice crystal structure. To put this in perspective, this critical cluster contains about 40,000 water molecules that must spontaneously arrange into the correct ice structure. Now let's understand why a gentle tap can instantly freeze supercooled water. When you tap a bottle of supercooled water, what exactly happens at the molecular level? The mechanical shock creates local pressure variations and cavitation bubbles that act as nucleation sites. The tap creates pressure waves that form tiny bubbles and imperfections. These serve as templates where ice crystals can form without overcoming the full nucleation barrier. These imperfections effectively lower the nucleation barrier, allowing ice formation to proceed rapidly. The free energy barrier for heterogeneous nucleation on surfaces is much less than for homogeneous nucleation in pure liquid. Once nucleation starts, ice crystals grow extremely rapidly, doubling in size within milliseconds as water molecules join the expanding crystal lattice. The freezing wave propagates through the entire supercooled volume in just a few seconds, creating a dramatic visual transformation. Let's examine the physics governing how fast ice crystals grow once nucleation begins. The growth velocity is proportional to the temperature difference below freezing, called the supercooling degree. As water freezes, it releases latent heat that must be conducted away for the crystal to continue growing. The heat release rate equals latent heat times density times growth velocity times the crystal surface area. As the ice crystal grows, it releases heat that flows outward. The growth rate is limited by how fast this heat can be removed through the surrounding liquid. The growth velocity approximately equals thermal conductivity times temperature difference, divided by latent heat times density times a characteristic length scale. For water supercooled to -5 degrees Celsius, typical growth speeds are around 1 millimeter per second, meaning a centimeter-sized crystal forms in about 10 seconds. An interesting comparison. Why does beer supercool more easily than plain water? Beer contains dissolved carbon dioxide gas and alcohol, which affect its freezing behavior in interesting ways. The freezing point depression equals the normal freezing temperature minus the freezing point depression constant times the molality of solute. The alcohol content lowers the freezing point to approximately -2 degrees Celsius for typical beer with 5% alcohol by volume. In beer, water molecules are mixed with carbon dioxide bubbles and alcohol molecules. This complex mixture requires more organization to freeze, making supercooling more stable. Interestingly, the carbon dioxide bubbles can act as nucleation sites when the beer is disturbed, triggering rapid ice formation and dramatic foaming. Is there a limit to how cold we can supercool water before it must freeze? Here's an intriguing question. Can we supercool pure water all the way to -50 degrees Celsius? The answer is that there's a theoretical limit around -40 degrees Celsius, called the homogeneous nucleation temperature. At the homogeneous nucleation temperature of approximately -40 degrees Celsius, water spontaneously freezes without any external disturbance. This diagram shows the temperature range. Between 0 and -40 degrees, supercooling is possible. Below -40, the liquid becomes so unstable that ice forms spontaneously without any trigger. At this temperature, random thermal fluctuations in the molecular motion are energetic enough to spontaneously create critical ice nuclei. This occurs when the nucleation barrier height becomes comparable to thermal energy, so delta G star approximately equals Boltzmann constant times temperature. Supercooling has fascinating practical applications in nature and technology. In meteorology, clouds often contain supercooled water droplets at temperatures well below 0 degrees Celsius. When aircraft fly through these clouds, the supercooled droplets strike the plane and instantly freeze on contact, forming dangerous ice that can disrupt aerodynamics. In cryopreservation, scientists use controlled supercooling to preserve biological tissues and organs without damaging ice crystal formation. In food science, supercooling enables rapid freezing that creates smaller ice crystals, preserving food texture and quality better than slow freezing. Let's visualize a classic supercooling demonstration you can try at home. Here's the procedure. Start with purified water in a very clean bottle. Place it carefully in a freezer set to -5 degrees and wait about 2 hours. Then, gently remove it and tap the bottle to watch ice crystals spread instantly through the supercooled water. The key requirements are using distilled water free of impurities and minimizing any vibrations during the cooling process. Important safety note, the bottle may crack from ice expansion, so use a flexible plastic bottle rather than glass. Let's dive deeper into the thermodynamics that makes supercooling possible. The entropy of liquid water is greater than solid ice because molecules are more disordered in the liquid phase. However, the enthalpy of solid ice is lower than liquid water because of stronger hydrogen bonding in the crystal structure. In liquid water, molecules move randomly with high entropy but high energy. In ice, molecules are ordered in a crystal lattice with low entropy but low energy. Below 0 degrees, the free energy change for freezing becomes negative because the enthalpy term dominates over the entropy term at low temperatures. However, the kinetic barrier from nucleation prevents spontaneous transformation, allowing the metastable supercooled state to persist. Let's examine what happens at the molecular level during ice nucleation. An embryonic ice nucleus forms when a few water molecules spontaneously arrange into the hexagonal ice structure. This small cluster is surrounded by liquid water molecules. For the crystal to grow, water molecules must rotate and orient themselves correctly to match the existing crystal lattice. The orientation timescale is inversely proportional to thermal energy, so molecules move and rotate more slowly at lower temperatures. Once nucleation starts, ice crystals grow extremely rapidly, doubling in size within milliseconds as water molecules join the expanding crystal lattice.